one small announcement. The head organizers wanted to put a sign-in sheet in the back, and we hope that you guys will sign in. It helps us figure out how the sessions are going, how attendance is working, and it's a form of feedback for us, and understanding the dynamics of the conference. That doesn't mean don't show up as a form of feedback. It's just sort of data, which is useful.
How about missing value?
Well, that's why we're making the announcement. Yeah. So yeah, help us avoid missing value. Great. And then no announcements. That's actually intentional. It was discussed beforehand that as a way of kind of abolishing any hierarchy, also giving more time for the talks. So in that spirit, I'll be quiet and let Joe take over.
Great. Thank you. All right, well, thank you all for coming early in the morning here. My name is Jo Hardin, and I'm a statistician. I did my PhD at UC Davis, and now I teach at an undergraduate institution called Pomona College, which is also in LA County, though it's still a ways from here. The work I'm going to be talking about today is joint with my senior thesis student, Benji, who just graduated. And totally unrelated to this conference, but very cool what he's doing. He just got hired by Harvard Law School to do data analysis for the state of Massachusetts. The state of Massachusetts has hired Harvard Law School to look at racial biases within their judicial system. And he gets to trove these data sets from all sorts of different places, which I think is a pretty cool job. He's very, very excited about it. Anyway, okay, so what am I going to be talking about today? I'm going to be talking about prediction intervals for random forests with application to high throughput data. So the majority of my research is methods development, in particular with applications to RNA-seq data and whatnot. I'm going to try to motivate this talk thinking in the context of that, but the particular results that Benji and I came up with and whatnot are all sort of simulated data, and they're not really high throughput data. So that's a little bit peripheral. But I'd like to actually just spend a minute with my title and think about how this conference or this workshop is being put together and who's here. So I think about prediction intervals as a very statistical thing, right? Because they've got that inference component to them. We're thinking about these ideas of a population and a sample and trying to make that inference. You take your data and you put bounds, you put percentile bounds, and that's what I'm going to be talking about today. Random forests, those are full machine learning, right? That's like computer science all the way, right? So making that link between a statistical idea and a machine learning algorithm. And then of course we've got the applications and how important all of these sort of statistical and computational techniques are for what we want to do in the biological context. So anyway, all right. So on to the statistics. I admitted to you that I'm a statistician, so right, that's where I come from for all of this. So this is what we do. This is my bread and butter right here, this slide. There's some population of something, and I have a sample of data. And I want to know about that population. I want to know about the structure of that population, and I have to get that information. I have to somehow be able to talk about that structure with just this one sample. And so this is what it looks like when I put those things on top of one another, where the grayed out points and the grayed out parameter line, right? For those of you who have taken statistics, you can think about that grayed out line as y equals beta naught plus beta 1x, and the dark blue line is y equals b naught plus b 1x, right? But that's the idea, is that we want to be able to get that structure. And there's two general ways that we think about getting that structure back in statistics and in sort of this linear regression context. The first way is through confidence intervals. And I don't know, your intro stats classes, which one of these you focused more on. But the confidence interval, the goal of the confidence interval is to capture the expected value of the response or the average of the response. So that gray band there is, we think about a confidence interval for the line, right? So for example, if I'm at x equals 0.75, I might want to know for all the things in my population, what is the average y value, what is the average response of all the things in the population at x equals 0.75. And that's that little red line. I don't know if you can see it, but hopefully you can kind of see that red line. And we're hoping that that red line, or the gray band, will capture that true line that is the population line, right? That's how we think about a confidence interval. Confidence intervals are typically done on parameter values, on averages, on expected values. Yay, it caught it for 0.75. Notice it didn't catch it down at the other end. We're not going to talk about all the reasons and whatnot, but generally you feel like that gray band is getting most of that population structure with respect to the average response value at any given x. But that's not our goal for today. Our goal for today is to capture the points. It's a different but related problem. So instead of trying to get at that band, what I'm trying to get is an interval that will capture the points. Okay, so now I have, lots of methods, statistical theory, that will tell me how to create an interval, again, at a particular x value, that will capture 95% of the points in the population who have an x value of 0.75. So again, we get to this point and we're like, oh yay, we get 95% of the points that have an x value at 0.75. Okay, this second type of interval, these are called prediction intervals, and this is what we're focusing on today. So we're not trying to get a sense of that prediction as a measure of sort of the population average. Instead, we're saying, okay, if you predict one response, how close is that prediction to individual responses, right? How do we have a sense of what that individual variability is? Okay, so everything I'm showing you is everything I've showed you so far is intro stats. Theory was developed ages ago. It's pretty straightforward, like linear algebra methods. So I didn't do any of that. That's just to motivate it. And really the question of the day is, what do we do when we're doing a prediction with something like a random forest and not a linear model that has all this theory telling us where those bands should be? All right, so before I get to this, let's motivate it a little bit in the context of this workshop. And I'm just going to give you a few references of people who are doing this. They're not doing prediction intervals, but they're doing random forests, random regression forests. Those of you who have some knowledge of random forests, you know that there's two types of random forests out there. There's random forests that predict a continuous response variable, a continuous y, and those are called regression, random forest regression. There's also random forest classification, where you're trying to say, is it healthy, is it cancer? And we're not going to be talking about the classification techniques. We're going to be talking about the regression techniques. So anyway, this paper, they were predicting lesion scores, and you can see that some of the other benefits of using regression is that you can really get a sense of which variables are most important, and they were looking at pathways where they had combined a bunch of genes. Their explanatory variables were pathways instead of individual genes, but they had these lesion scores that they were trying to predict. Okay, a second paper is using cell lines in the NCI 60 data set, and they were measuring drug sensitivity, and that's what they were trying to predict. And this is actually a methods paper where they're talking about how you can kind of nest different random forests. So they have this series of random forests that they do. But again, they're trying to predict this continuous value. And last week, Jennifer Listgarten talked to us about gradient boosted regression trees, which are sisters to the regression, the random forest regression. And one of the things they're interested in, again, is this idea of of variable importance, which is what this bar chart gives us a sense of. And in the sentence right below the bar chart, Gini importance refers to the decrease in mean squared error. So that's going to be a really important feature of what we're doing. So there we go. So regression trees in high throughput data. Okay. Now we need to develop this idea of prediction intervals for random forests. So now I'm going to give you a series of plots that, or actually it's the same plot over and over, but it's got some lines on it, or it will eventually. And what I need you to know from this plot is that my data set, I think there's 50 observations, 50 points on this scatter plot. And there are two x variables, two predictors, x1 and x2. And you can see those on the x and y axis. So I do not have y as one of my axes. I don't have my response. Indeed, the response is the color. Okay, so that's what you need to know here. It's just 50 points in 3 dimensions, your response, and then 2 x variables. But you can see that even just with a few points here, in the bottom right corner, there's a large response, right? Light color means high value of y. And in the top right corner, there's a large response, right? And so then, but then in sort of the middle there, like you can see, what you can see even in just this plot is that there's not going to be a linear function of x and y. And in fact, I simulated this data as just a quadratic function, just to get us past the idea that linear model, I mean, you could do a linear model with a quadratic on the x variable, but right, we're just going to apply a random forest here. Okay, so as is typical with random forests, the way we're going to really think about variability and how these points differ and whatnot is through the sums of squared error of the response variable. Okay, so in the bottom left corner there, I've defined this, and I've just said we're going to take all these 50 points, we're going to predict the we're going to give a prediction for them. Now, because I've done no modeling whatsoever, my prediction for every single one of them is going to be the average y value, okay, because I haven't done anything yet. So everyone is going to have the same predicted value, and I'm just going to measure how far the y value is from the average y. I'm going to add those up for all these points. So this is just sort of a baseline. What if I didn't model anything? How would these points vary? All right. It is. So that's right. So so that y hat is so sum of squares error is going to say how good is your model, okay? And y hat is going to be my model, and this is step 0. I haven't modeled anything yet. Okay, so step 0, I haven't modeled anything, and therefore I don't know anything about the x's, and therefore my y hat prediction is just going to be y bar. The straight average, it's like a baseline. What if I didn't know anything? What if I didn't have a tree? What would my sums of squared error be? Yeah? Okay. So now what I'm going to do, that first step of let me take one more step back. Random forests are built on what we call classification and regression trees, CART. So what I'm going to do is I'm going to walk you through what a regression tree is, and then we're going to talk about how a forest is an agglomeration of trees. I have to say the machine learning community does an excellent job at naming things. Like the names of what I'm going to show you, it's like, oh yeah, that's a tree, and you put them together, that's a forest. Okay. So anyway, what I'm going to show you right now in these next few slides is how one builds exactly one tree, and then we'll put it together as a forest. Okay, so first step, what do? I simply partition this space such that I minimize that sums of squared error, okay? And now by partitioning this space, I'm going to find the average of the points on the left side, the average of the points on the right side, and those will be my y hat. Those will be the values that I'm using to predict everything in that space. So you can see that when when I didn't have a model, my y hat was 89. Okay, that's what you see over there on the tree. Now when I partition these two groups into, two different spaces, I see that for all the points on the left, I predict them to be the number 73. For all the points on the right, I predict them to be the value 145. And the sums of squared error for the left points is 806.6. The sum of squares error on the right points is 879. 800 plus 879 is less than 1705 or whatever that, 1705. So I have found the partition rather, 7.6, that will minimize. So the computer, what did it do? It took that line and it just went back and forth, or really it just went one way, right? And it looked at every single partition. And it looked at every single partition in the X2 space, and it said, this is the one. This is the one that's going to minimize that sum of squared error in terms of partitioning the space. Okay, so then I do it again, and I found my next one. So my next partition happens at X2 at negative 7.1. And now I have three groups. I have three separate y hat values, right, predictions. In the top left corner, I predict all those guys to be 64, which is the average of those points. In the bottom left is 113, and then the top right-hand side is 145. And you add these up, they will be less than those two 800 values added together. Again, I have minimized that sum squared error.
Joe,
yeah.
In each square, a resultant square, like you do, you could either partition by x1 or x2.
That's correct.
Okay.
That's correct.
Effectively.
So yes. And the algorithm will continue to look in both spaces recursively, right?
It will also continue to look in both.
Yes, and it will continue to look on all nodes of the tree.
Right.
That's right.
Only separately, x8, either x1 or x2, not any combination.
Correct. Correct.
Linear, not polynomial, not
It's not linear, it's not polynomial, it's not the product of x1 and x2. It is vertical and horizontal lines. It looks at every single partition in every single one of these rectangles, everywhere along, but not any kind of functional form of them. That's right. We can keep going, right? So, this is a regression tree. A regression tree partitions the explanatory space, right, the X space, such that we minimize the sum of squared error between the y values, the response variable, and their predictors, where the predictor is simply the sum of the points in that space. And these predictions can happen in any dimension. Again, they just happen one variable at a time, so you can draw these hyperplanes in 20 dimensions, and the tree will look just like that. Yeah?
But you could be splitting the other.
Yeah, it just happened to be that the right-hand branch didn't ever split again.
So what criteria do you use to stop splitting?
Great question. Okay, so there's a series. There's a lot of different ways that you can decide how to stop the tree. In CART, you definitely want, CART is classification and regression trees. If you're building just one like this, you definitely need to think about that question very carefully. Okay, so otherwise your tree will overfit your data, right? Because eventually your tree will just find the points, right? It'll just have points at the end, which is kind of a silly model. We are going to use an agglomeration of a bunch of trees. And so that particular criteria is not as important because we're going to be averaging. And typically in random forest, the criteria we use is just node size. So we say we don't split a node if it has fewer than 5 observations or we don't split a node if it has fewer than 10 observations. And certainly there will be some overfitting to each individual tree with that criteria, but when we agglomerate all the trees, that overfitting goes away. And you'll see that in a minute.
People just sort of have a criterion that is based on the number of points you have in each tile, as opposed to the overall level of standard error that you reach.
Right, so this SSE value is really dependent on the units in which you're measuring y.
Which you could have standardized away.
Which you could have standardized away, but like the number of points in there, like there's so many sort of.
So it's a number of points for, say, avoiding gross overfitting.
That's right.
As opposed to classification performance.
That's right.
Or
That's right.
performance.
That's right. Exactly. Okay, so let me just stop here for one more minute to think about what I would do in this context if I had a new point. Because that's sort of where we're going with this prediction interval problem, right? I have a new data set. I have a test value that comes to me, and I want to be able to guess at what its prediction is, right? At what its response is, right? So I'm going to predict that value, and then I'm going to put some confidence limits on it. So let's just stop here and think, how would I predict that value? What would I do? Okay, so I have a new point, and let's say it's at 6,1. So it lives, at 6,1. It lives right here. So, I mean, I can see it in this plot quite easily, but sometimes you have a large predictor space, 20 dimensions, and you certainly would not be able to draw this plot. So you just follow down your tree. So you say, okay, my x1 value is 6. It's less than 7.6, yes, comes over here. My x2 value is greater, yes. My x1 is less, no, okay. So my prediction for a new point that lives at 6,1 is 89. Yeah? Okay. Okay, so a random forest now is just a lot of trees. That's all. And so what I do to get a prediction from a random forest is exactly what I just told you. I get that number 89, and I do it through all of my trees, and I average those values. Now, okay, I haven't told you how my trees are different yet. I'm about to do that, right? But let's say I have slightly different trees. I can take my new point, and I can follow it down the tree. I get 89. I follow it down the tree. I get another number, and I average those points. And all these questions that we've had about, how deep to run the tree and whatnot are okay because I'm doing this agglomeration. This random trees are also called boosted aggregation, which is called bagging, if some of you are familiar with some of those words. Okay, so here are the two really important features of random forests, which are which is what leads to having different trees. So the first feature is that at every split, which means every single time I go and I say, should I break this node apart, I don't consider all the variables. I only consider about a third of them. And this is a really important feature for data sets that have large number of variables. Okay, obviously if you had the same variables every time, you've got a few variables maybe that are really highly correlated with your response, so they're going to be driving that tree every single time. They're going to be driving that sums of squares error. And so this first thing, doing this decorrelates these trees so that you can kind of get sort of a good sense of what's happening in the entire predictor space. So this is, again, really important for creating different trees, also really important for random forests on lots of variables, but it is not important for the specifics of what we're going to be doing today. Okay. The second thing that makes these trees all different is that we bootstrap the data. Okay, so every single time I build a tree, I do not use the original data. I use a bootstrapped data set. Okay, what is a bootstrapped data set? I think I have it in the next slide actually, but a bootstrapped data set means that, let's say I have 1,000 points. I reach into my bag of 1,000 points. I grab a value. I write it down. I put that value back. So then I grab a second value, I write it down, I put that value back. I do that until I have 1,000 new points. What that does is it creates a data set of 1,000 points, which is very similar to my original data set, but it probably has some replicates in it, and it has some missing points. Okay, so those of you who are familiar with bootstrapping, I'm going to talk about it. I'm going to talk about it again in a minute. Are used to this concept. For those of you who've never seen bootstrapping before, this kind of blows your mind. There's so much about bootstrapping that can blow your mind. It's really fantastic. But the idea is that when you bootstrap, some of your data does not go down the tree, and therefore, they don't build the tree, they don't train the tree, they are an independent assessment of that tree. Okay, so the bootstrapping does two things, and these things are really important for what we're going to be talking about today. The two things that it does is it creates different trees because it's using different data, and it creates points which do not go into the building of that data and therefore can be used to assess the tree. Yes?
So let's say that these are two different types of stochastic perturbations that can be used to create a variety of trees, move the tree.
That's right, exactly.
Are they used always together, or one uses one or two?
So this is what people mean when they say random forest.
Both of them?
Both of them at the same time. When people say random forest, they mean that both of these things are happening. I don't know the history or sort of the literature, whether one came up and whether some people think one is more important. You do?
Bagging is just the second one.
Bagging is the second one.
Just the second one is bagging.
Right.
And first, and both of them is on.
Right.
By the way, the names were invented by statisticians.
Oh, good.
And then Friedman and the guy who invented the names. And random forest is Brian.
Is Bryman? I thought he was a computer scientist, though. No, he's a statistician.
You're a mathematician who became a statistician.
Nice, nice, nice. All right, here we go. Okay, we're moving on here. All right, so let's think about what happens here. So there's a couple things I want to talk about in this particular slide. So the first is what I've been, the left-hand sort of tree forest structure, rather, is what I've been talking about. You have some training data, and you create all these trees. And the gray nodes are the terminal nodes. Can we see that? That the gray nodes are the terminal nodes. So those gray nodes are the ones that are going to, all the points that end up in these are going to be averaged such that we get a predicted value, and then we average again over the trees, right? So like this node, this clear node is, going to be split again. Okay. And for each one of those trees, we have done these two stochastic perturbations. I like that word. So that they are different. As you can see, they're different. Okay. Now, let's stick over on this training tree for just a minute and think about what happens with the bootstrapping. So I've already said this, that bootstrapped data means that we resample the same number of points. So if we have 1,000 data points, we resample 1,000 new points with replacement. Again, that means that you can get duplicates rather, in your new bootstrapped resample, and that there will be some points that get left out. In fact, it's pretty straightforward. You can show that every time you bootstrap, you get about 2/3 of your observations, and you leave about 1/3 of your observations. So that means in every tree, 2/3 of my data are used to create this tree, and 1/3 of my observations are not in this tree.
Why is that?
I don't know. I mean,
1/3.
well, it's not actually. It's like 63%. It's not 2/3 and 1/3 exactly.
Just the expected number. Just the expected number.
It's just the expected value.
Distinct elements.
Yeah, it's a combinatorics problem that I've seen but can't replicate. Yeah.
1 over E. Yeah, 1 over E.
Oh, 1 over E. There you go. Okay. So that means that so for a given data point, right? For a given data point, it will train 2/3 of the trees. and it will be independent. It will not train 1/3 of the trees. Yeah? Okay. These samples, when you have a training observation that does not train the tree, we call it out of bag. So an out of bag observation means that it was in the original training set, but that it did not train a particular tree. Okay. We also have test data, right? So we've got to get in our heads like 3 sort of types of data. We have our training data and our test data, but our training data, you know, depending on which tree we're talking about, some of them actually trained the tree and some of them didn't. Our test data, totally independent of all of that. The test data, we get predictions for all of the test observations. So let's just say we have one test observation. What is my prediction for that new test observation? Well, I let that test observation go down the tree. I just say, you know, is it less than this number, bigger than this number, all those things. I get to this terminal node. I go back to my training tree. I say, who lives in that node? What are their average response variables? What is that average Y? That will be my prediction for that test observation on this tree. I do that for all of the trees. I average those numbers to get the prediction for that X value. Yeah?
Since data usually is precious, and you know, test data you may or may not want to use as test. Do people cross-validate this having yet another layer, or do they use the out-of-bag thing that is sort of implicit in this mechanism to create out-of-sum polling
right
within the mechanism?
Right. So what I'm, you know, about to get to, right? 2 more slides, is this idea of prediction and an interval, in the sense that I actually, if I were doing this to actual data, I wouldn't know why. Yeah. Right? So the goal of this work is to be able to come up with an interval estimate for a data set in which I have the X variables, but I don't have the Y variables. So in that case, my test data it would be of a different flavor than my training data, right? So I would be very much in the situation that I had these new test observations, where do they live, you know, and I have my training observations. So the training observations, the cross-validation actually, because we've got these out-of-bag things built in, we don't typically see additional layers of cross-validation. Okay, so now we come back to our original problem. The idea is that we want to predict, if I have a test observation and I put it down my forest and I get a prediction, well, is that prediction that plus or minus 1? That plus or minus 10? That plus or minus 100? Like, how do I have any sense of the number that is related to this new test observation that I want? So what my work is on, now we've gotten to my work with Benji, is creating sort of an error. We call it the mean squared prediction error for that prediction of a new test response. So MSPE2 is something new that we've come up with. MSPE1, for those of you who are familiar with this, it will look very familiar to you, but it has not been used ever, to our knowledge, in this context. So MSPE1 is something that's in the literature, but not in this context. So as far as we know, we're the first ones to use this idea of creating these intervals. All right, so how are they different? I'm going to give you some formulas and whatnot. But before I get to the formulas, let me just kind of explain the difference between an overall measure and an observation-specific measure. So there are times at which there are times where it's better sort of to aggregate and to come up with sort of an error for all possible x's, and there are times when x varies quite a bit. And let me give you an image. So some of you may be familiar with pictures like this from your intro stats classes where you have really strong heteroscedasticity. And this is just an XY plot. So X on the X-axis, Y on the Y-axis. And you see that for small values of X, your prediction is much smaller than for large values of X. Right? So in this case, we would want that second error measure. We would want a measure that is specific to the predictor space, because we would say that for particular X values, my Y is closely varying. And for other X values, my Y is widely varying. Okay? So here we go. This is the only really equation slide. So here's the formula of these two, here are the formulas for these two measures. The first one is the measure that's used for assessing random forests. So what is it? So let me also say that mean squared, both of these values are calculated from the training tree. All right, neither of them are functions at all of the test data. Okay, so we get these numbers from the training tree. The first one says, take the yi values, all of the n values of yi, and say how far are they from the predictions. So we've already talked about what the predictions are. They are, let's ignore this word cohabitant for a second. It's the predicted response for the ith observation using all of the trees for which I is out of bag. So that's about a third of your trees, right? A third of your trees will not have been trained with I. So take those third that I did not go into, and that is your prediction. All right. Now, if we're back in this case of heteroscedasticity, right? Well, maybe we don't want every value to be assessed with all of the response variables. So what can we do? We can say, okay, give me my new test observation. Tell me where my test observation goes. Call the points in this node the friends or the cohabitants of my new test observation. Okay, so I look at this node for this particular test observation and I say, who lives in that node? This is a cohabitant node. And I say, okay, repeat that process of out of bag, but do it for out of bag cohabitants. Right? Only look at the trees for which, remember my tree is like the X space. Only look at the trees for which my X space is consistent with the particular X I'm interested in. And that's what MSPE2 is. It's the cohabitant trees which are also out of bag. Okay, so the CI is just a way to weight it to make sure that we're getting we're counting appropriately the number of times. So notice that both of these error rates are calculated using the training tree, although MSPE2 is a function of the test observation, simply because we had to know which of the trees in the training forest were the ones that were going to go with that error rate. Yeah.
Can you repeat the definition of cohabitant?
It just means that I took my training point, and I put it down every single tree, and I said which points are in there, right? So it's 2, 7, 94, and 343, right? And then this guy, it was 2, 7, and 56.
So you just take a set of all the points that appear in the leaf.
The node, right? Yeah.
Okay. They're the cohabitants.
They are the cohabitants. Yes.
So what are the cohabitant
So I take,
Do that only for the trees, for the out-of-bag trees?
yes,
Okay.
yes. So the cohabitant out-of-bag trees.
Yeah.
Exactly, that's exactly right. So I don't want to spend a lot of time getting on the details of the calculations of it, but the idea simply is that we want to find the points in the training set that look like this test value,
Yeah.
and do the out-of-bag independence stuff with them.
I see. So then you take this set of points.
Yes.
And do the out-of-bag
Predictions. That's exactly right. Right, that's exactly right. So again, just kind of thinking through what are these things, it's just saying, I have a new test observation. That test observation lives in a particular space of the predictor variables. Find the points that look like that. And we find those points using the tree mechanism, not using like Euclidean distance or something.
And do the union of neighbors across all trees?
The union of neighbors. No, we say.
Neighbor or cohabitants for each tree, right? So,
But again, is it 1 point, is it neighbors or 1 point per tree?
No, in each tree, there's going to be a bunch of points in the node. Yeah. So for that tree, for each tree, if it's cohabitant and out of bag, then we use it to get this prediction. That's the key, right? Because we're summing over y equals 1 to n, right? So for
N is not the number of trees.
n is the number of observations. So if you are never a cohabitant of me, then ci will be 0, and I will never use how far you are from your predictor space.
So this
Yeah.
mechanism, for the second definition, is what makes the evaluation of something variability local.
Yes,
in terms of
exactly.
X
Local's a
difference,
great
maybe
question.
Bigger for some
That's right.
X neighborhoods and smaller for
That's
other
right.
X neighborhoods.
That's right. This is a local way of measuring the response variable. This is a global way of measuring the response variable. Exactly.
So the trees are just a data structure to facilitate this.
Yes. Yes.
So this is some combinatorial or statistical criteria. It's not, yeah, but the tree just facilitates that search.
You could do all this with Euclidean
Exactly.
distances and
You
least
can
squares,
go
but this
with
is a smarter way of,
Yeah.
in some circumstances.
So Sharon first. Yeah.
So just to make sure, XH, the MSPH2 is a function of XH.
It is.
So it's for every point to get a different measure.
That's right. Yes. Thank you. Yeah.
Analogy to nearest neighbor, you think you would do first average and then calculate this probability.
Well, okay. So I'm not going to be able to. So nearest neighbors assumes you have a distance metric. A distance metric. What does it mean to be near to me? Right? You've got something in your head that's measuring that distance metric. And I don't.
You can use this as a metric, right? Based
In nearest neighbors?
on cohabitation,
That's interesting.
Yeah.
It produces a true distance in some a true metric or a true distance.
Is it a metric? Yeah, is it a metric?
I don't know.
There is an unsupervised version that actually has an approximation matrix, which is basically distance, and you could use that for other things.
Yeah, but it's good that it's supervised. The response is guiding the metric based
Yeah. That's right. That's right. Okay. We're going to keep going here. So anyway, okay. Right. So then what do? We do exactly what you think we're going to do, and it's super ad hoc, and we're just going to say plus or minus 2 copies of the square root of this thing.
Why not 1.96?
Why not 1.96? Right, exactly. That's exactly right. Okay. So here's some things that are worth noting. The first thing is that these actually produce intervals with remarkably good coverage rates, right? We're getting really close to 95% for both of these in lots of simulations on simulated data as well as on data that were just publicly available data sets. Okay, remark number 2, I'm going to show you some plots and stuff for all of these, but remark number 2 says that the first one is less variable than the second one, which sort of makes sense because if you remember, the first one uses endpoints to calculate that error, and the second one uses only the cohabitants. So it uses fewer points. So just in a, in a S over root n way, right? Like you have fewer things going into your calculation of this error. And then remark number 3 is what we were just talking about, and I'm going to show you some plots, is that this first one estimates the overall prediction error, where the second one estimates the prediction error of the individual responses, and we see that in the simulations. Okay, so what do the data structures look like? We've done a lot of different things, but I'm just going to try to only show you a few things. I'm just telling you about the public data because I give some results on that. So those of you who might be Boston, this is it's a housing data set, housing prices, and those other 2, forest fires and ozone, those are in the UCI machine learning repository, whatever. So this is basically the structure of the simulated data that I'm going to talk about today. It's these clusters which we feel like are good for random forest, right? Partitioning. These are all in X space. So this is, X1 and X2 and X2 and X4. We're looking at these again with the response. I'm going to talk about 2 different clusters. One where all the clusters are centered at 0, but they have different Y variability. And the second where the clusters are centered far apart, but they have similar sort of variability structure like that picture. In like 10, I think we did it in 10 dimensions. Okay, so accuracy. These are actually 2 different pictures. I know they don't look like 2 different pictures, but there's a place where I can show you that they are. I double checked.
No, actually, the intervals are
Cluster of points is clearly different.
Yeah, here we go. This orange point is above the line, and this orange point is below the line. There we go. Okay, so this is the situation where we're talking about clusters. So remember what the goal is. The goal is to capture the Y, not the expected value of the Y, where the center of the cluster is going to be where it gets predicted, and you see that. You see that, all the points that sort of had this spread, they all got predicted to this value, but, this point, its true value was here, this point, its true value, was down here, right? So it's not about getting, so those black points are the Y hat values, but we want to make sure we get the true value. The x-axis is the true response, and the y-axis is the predicted response. I don't know what it says there, though. I can't read it. I'm sorry. Mean prediction. So is that the black point, maybe? Okay. Anyway, so you want this diagonal line to go through the confidence interval. That's what we want. Those intervals are those prediction intervals that I was just talking about. So you want that line to go through the prediction intervals. And you see in this case, we had to find specific points where these 2 plots are different. They're not really that different. And you can see that they don't always capture, right? So there's a little orange point here. So this interval is not capturing that true value. But generally, we do pretty well. So these are our capture rates of the points and over lots of replications. And I'm not going to spend time because I feel like I'm already way over going over how we did all of the simulations. But in parentheses are the standard errors of the capture rates. Okay. I'm not going to. So in the interest of time, I'm going to skip this. But this just says that one is more variable than the other. Okay, and then I'm just going to talk about this for 1 second. So this is the case where we simulated 5 clusters. All of the clusters were centered at a response variable of 0, but in different predictor spaces, right? And the Y value was much more variable in some of the clusters than in others of the clusters. And you can see that when you use MSPE1, by definition, the error is the same width. Yeah. That's how we defined it, and you can see that happening. Over here, what we can see is that for some of these clusters, we get that correct, because remember, they live in different X spaces, so we can find them in our random forests. So for some of these, we get that really close bound, and for others, and then for the ones that are really far away. And what you see here is that in the MSPE2 situation, that the far away, those wide clusters, have larger standard errors than in the MSPE1.
And you don't make mistakes.
Because this one's going to make more mistakes.
Exactly.
Right.
And in fact, there are more red.
That's right.
Above.
That's right. That's exactly right. See, because these error rates, by definition, had to average out these small ones and these big ones, well, it caught all the ones in the middle, but then it missed all of these ones on the outside. Okay, so we're still finishing up some of our simulations, and what the main point of the simulations is to understand the properties, as I gave you by those remarks, understand the properties of these estimators. And in particular, we've focused a little bit on clustering, and there's some other kind of interesting things with respect to the linear structure. And for example, that one picture I showed you with the heteroscedastic linear structure. So really kind of understanding the properties of those two things. We're also sort of talking about this, though I don't know how much progress we're going to make, but really thinking about what goes into that error, and that there are really three pieces that go into that error. So it's the variability of the predictions, right? How far is that y hat from the y in a variability sense? And then, again, those of you who work with random forests have quite a strong regression to the mean effect. And so there's a lot of bias in those predictions as well. And then, of course, the variability of the observations around their true mean, right? So understanding, we feel like we've measured this in a very direct sense, and our results and our plots and everything show that we're right. We're getting exactly what we expect, but kind of thinking about why and how that measure can be broken down into these three pieces is something that we're interested in. All right, there you go. Thank you so much.
Take a couple minutes for questions.
So, can you return to the previous slide? And you say the theoretical derivation of the MSPE. And what I was wondering is that it looks to me, again, I'm not a statistician and everything is new to me, but it is quite arbitrary, the partitioning that you are doing, and instead of just any partitioning, okay? Because, come on, you're talking about the points in space, and why exactly these, okay, but without any consideration of any joint.
So you're
exactly. So my question is are you into? It's a question. Are you into theoretical derivation of why this arbitrary what that gives you?
No. Okay. So the question you're asking, I hear you, is like why those particular partitions and why not something sort of more fancy, and how that then impacts this MSPE2. So really your question boils down to like why random forests, and I don't know all of the literature on random forests, but what I do know is that these methods, this idea of bagging simple things, has proven to be incredibly effective in sort of the machine learning literature. So the simple models that are used in a stochastic perturbation sense are often far superior to more complicated models. So I'm not trying to when I say derivation, I don't really mean derivation from first principles, because the stochastic pieces that go into this, like if I was trying to write a probability model associated with the 1/3 variable or whatever, but not really theoretical, but just kind of pulling out those three and where are they coming from and how are they measured. But I'm not going to be able to answer your question of like why random forest. Maybe Francesca, please.
For instance, you could do partitions making the line.
This is function of
This is a very profound difference in philosophy and statistics. What this does, it uses the original feature. It doesn't create combinations of the original feature. And some people way prefer this because it's more interpretable.
Yes,
that's true too.
Give some bounds just assuming, okay, I look only on one variable, not any combination, and that will give me at least this and that, given the stochastic model I'm asking, I don't know.
So this is one explanation, is interpretability. You know, there are statistical methods that stay close to the original features. There are statistical methods that get fancier and take linear combinations or even nonlinear functions of the original features to improve.
But Francesca, I would argue a little bit back on you because we're aggregating these trees. So you do lose quite a bit of the interpretation when you aggregate the trees. But there are ways of talking about the percent of variability explained and stuff like that.
One tiny comment, this is still a forest.
Sure, it's just a different forest.
But it's based on...
Yeah.
Can I make comment on that? Then there's huge literature on trees, and people have tried doing multivariate splits and looking ahead and all kinds of things. And these simple things remain dominant.
Yeah, that's my understanding.
Cultural and performance reasons, I guess.
So I'm not familiar with this tree, so I'm learning something new today.
Great,
Thank you very much.
great.
Now you start with linear regression, right?
Yes, but that was just for your sake. I mean, not your sake, but everybody's sake.
Let me finish answering
Sorry.
the question first. That you can think of as a maximum likelihood
Yes,
associated with a particular model,
yes,
a linear Gaussian model.
yes.
But when you propose this random forest or forest, you didn't give a model.
Yeah, that's right,
So
exactly.
what is the model for which this is an optimal?
Right,
procedure?
yeah, I don't know. So, right, so this is again that confluence of these ideas of statistics where things come from a model and their optimization, it's maximum likelihood or whatever, versus a machine learning technique that's very algorithmic. So random forests were not derived as an optimization in any way. Somebody's going to correct me. Maybe they were, but not to my knowledge.
Something algorithmic.
Sure, but
I'm emphasizing on the model.
but I
There exists a model
don't.
for
Right.
This is some sort of
Somehow
optimal
optimal.
procedure for.
That's a good
I
question.
mean, you can definitely think of this as a search in a function space, where the function space here is a set of all trees, or in this case,
Yeah, that's
set
the
of all
empirical
forests.
risk
The empirical risk,
minimization
but people-
formulation,
Yeah, and people have looked at that.
but not a statistical formulation. Though. It's not with respect to a
It's a
particular
universal
model.
approximation, right? So that's a statistical.
Sorry?
Asymptotic statistical notion, having universal approximator.
Right. But it's not in the same sense as the regression be the maximum likelihood of a linear one.
Right.
Yeah, but for empirical risk, you can also cast linear regression in that same empirical
Yeah,
risk formulation, and so there is a unifying formulation for considering all of these different models.
And one technical question, I'm stuck on the cohabitation. So that cohabitant coefficient, does that count also the number of times each point is a cohabitant?
Yes.
Okay.
Yes.
It's not just the binary.
No, the number of times. That's right. Yeah.
Thank you for the talk.
Thank you.
So what I was understanding from the talk is that you're interested in finding the confidence intervals for the
Prediction intervals. Let's call them prediction intervals.
prediction intervals for the particular y values and not the mean value.
Yes.
So for in the simulation plots, when you showed the MSP confidence prediction intervals, what was the black solid line, and if it is the mean prediction, why you are interested in that? Because that's not of any interest anymore, right? Just
The true response is let's find one that we can know. Okay, right. The true response is this value, and so we want to know if this point, so here's the mean prediction, here's the black point, right, and then here's the interval. So did I get the true point? Did I capture that line?
okay. So the black solid line is the true.
It's just y equals x.
Okay.
The black solid line is y equals x, so therefore it's the x coordinate. I'm sorry, I didn't make that clear. Yeah. Sorry.
Great talk and a lot of good stuff. So let's thank Joe.
Thanks, John.